Okay, so let's start with yeah, so since you saw them, I think mainly what I want to go over is what the proof technique for each of these should be. So I'm looking at the combinatorics problems, start with number two. So it's number two. This is from IMO 2022. Um, yeah, so I won't copy the problem, but it's the one about the Bank of Oslo. Um, let's see. Yeah, so can maybe you can explain one of you who solved it what the idea is.
Um, so first, any number less than n wouldn't work because you can just put less
No, strictly less.
less than circles because you can just put k is and then put anything else such that first numbers aren't always.
Great. So this will get stuck. Um, good.
Hmm. And as for the highest bound, I think um, I don't remember what it was exactly. It was like three and or 3n divided by two floors or seals. I don't know, but
I think it was
the argument is basically you can keep that number of, uh, that for the number of let's call them segments or whatever. Uh,
okay.
or connected components, I think. So, and the number will keep decreasing. But if you want uh,
So let's make a definition, right? So the definition you called it um, connected components. So let's say so you called it sigma. Define sigma is the number. Um, let's use the wording from the problem. They say it's a chain, right? So let's say the number of chains. Okay. And your claim is what?
um, if it decreases, it can. Um, no, if you want it to continue forever, it should stop decreasing at one point.
Great. So I guess yes, the fundamental claim is that this quantity will decrease every step, and then I guess yeah. So it cannot go below zero. Um, well, let's be a little bit clear. So it decreases every step unless um, unless what?
Um, unless the number doesn't work. Also, not necessarily every step.
Sorry, say again.
Uh, not necessarily every step.
Uh,
Um,
so we're assuming n is here, right? So you said there was some upper bound or something.
yeah.
Maybe it was.
Um, You should divide into four chains. So,
Uh, I see.
it
So
would be the it would be 2n minus the size of the smallest segment
two n.
chain.
Mm, mm, let's see. So
and divided by 4 fourths.
like this.
Yeah.
Okay, let's see. So, and then the claim is it does not work for 2n bigger than that.
Yes.
I see. Okay, so maybe yeah, maybe we should prove something, right? So let's see. Um, so then you're saying that for the okay, so you're saying what is the claim? So sigma is the number of chains. This then sigma will so let's just say sigma will decrease every step. Um, so that's almost true, right? We have to be a little bit careful with the statement. Um, it will decrease unless we're in this like end state, right? Like if you ever have
E.
like if it ever becomes
Okay,
like
I think we can use the extreme principle.
uh-huh.
Or yeah,
Well,
we
so
just
but before we prove the claim, I just want to make sure the claim is correct, right? It'll decrease unless we're here, right? That then it won't. Like if it becomes all A's and then all B's, then it stops decreasing, right?
um
Is that correct?
Is it better
uh,
to just say it never increases instead of always decreasing?
Okay, maybe it's safe we
yeah.
can say it like this. Will never increase. Okay. Okay, so now there's one thing. Let's see. So now the point is, what if it gets stuck at some number, right?
Yeah, so I think we can assume that um it's stuck at this number uh, and then I think we can solve this. So
Mm-hmm.
um if it's on any chain other than the last chain
Mm-hmm.
to the right, the number of segments should, the number of chains should decrease.
So maybe we can say it like this. So I think we're going to say will decrease unless mm, unless maybe we can say the kth coin is in the last chain. Is this the correct statement?
Yeah,
Okay, so I think
that is of course when k is greater than 1.
so that is when actually this is always true, right? They don't need to say any condition on k, is that right? No. You need to say k. Is this always true or is there some condition on k?
Uh, no, so it's just so since the since with 3 chains, nothing any move will one will or yeah any move will work. We will assume that we have 4 chains to maximize their size.
So you're saying, am I considering something like? Sorry, I'm a little. Are we considering something like this or?
Yeah.
Yeah. Mm, mm, mm. Okay, yeah. So I'm a little. So how do we deal with this situation? Yeah.
Maybe we
Mm-hmm.
need to consider both cases for sigma as a even and odd, because like if it's odd, then the first and last segments will be the same.
Mm-hmm.
So for the even one, I mean for even sigma, we have the another case you have to consider.
Okay. So you're saying, yeah. Okay. So I see. Yeah, so you're saying, okay, maybe yes, you're saying you could define sigma as the number of chains. Sigma will decrease unless the kth coin is in the last chain. Sigma will also decrease if sigma is odd. Maybe this is correct?
Yes.
Okay. Yes, maybe we can sort of, okay, let's make this a more clear of a statement. If K is in the, sorry, if the kth coin is in the last chain, then um, then sigma will decrease if and only if sigma is odd. Okay, so maybe this is the correct statement of the lemma. So maybe let's call it a lemma now. So is this the correct, so this is maybe the correct statement of when sigma decreases, it will decrease either if the kth coin is not in the last chain, or even if it's in the last chain, it'll decrease when sigma is odd. Is this correct?
Yeah.
Okay, great. So let's so there's two things we have to do. One we have to do is we have to prove the lemma, and two, we have to use the lemma to solve the problem. So maybe let's first use the lemma to solve the problem. So how do we do this?
I think we can just assume we're in that stuck state. So we know
Okay. Okay, so assume
the number of chains is even, um, and the smallest chain is at least to n minus yeah, to n minus k.
and then you're saying furthermore, the what? The last chain.
No, all chains are greater than 2n minus k.
Um, I see. This is because, I see. So this is because so it does not decrease anymore, let's say. So the fact that it's not decreasing anymore tells you that this statement is true. Okay, right. Um, okay, great. Then what do I do?
Now, since we're trying to maximize the size of the segments, we may as well just uh, assume uh, sigma equals 4.
Hmm. Okay, so now we're saying assume sigma equals 4. Uh, hmm. Um, hmm. Maybe we can just say, okay, and then you're saying I need to say
I
2n.
think we can, if you want it more formally, we can just say that if it works for sigma equals some other even number greater than 4, then it also works for 4 because we can just combine chains and their size will increase.
Okay, but maybe what is the argument for sigma equals 4? Maybe we can just, yeah, maybe I think you can say what that is.
Um, if it, if it works for anything other than 4, then it should also work for 4, so we can just assume that it works for 4.
So once it works for 4, what do we say? What's the argument?
Um, Now, if it doesn't work for 4, then it doesn't work for anything else. So it only works if it works for 4.
Yeah, but so let's say it like sigma is 4 and it gets
Oh
stuck,
yeah,
but now you have to show something
the
about k,
size
right?
of okay,
Mhm.
so we should divide 2n by 4, and the maximum, yes, to get the uh, maximum size of the small segment, so that would be 2n divided by 4 floor.
Or um
Uh, plus 1, I think. No. Yeah, no, without the plus 1.
okay, without plus 1.
So 2n minus k should be um, less than 2n divided by 4.
Is it less than or less than
Less, without equal.
uh
Uh,
oh, okay, I see.
strict
Yeah,
less.
yeah, strict. Okay. Okay. And now I'm wondering, is it yeah, so you're taking the smallest. I see. So this is the I see you're saying um there exists some chain of this size, and so okay, 2n minus k should be less than that. Okay, great. Yeah, good. Um and now maybe I'll make a point, which is you don't have all this thing about sigma and so let's okay, what is the point here? um, Assume sigma does not decrease anymore and sigma is not 2 because we're trying to because otherwise we'll be in the this AABB state. So then the point is then you can just write here, maybe instead you can write um, you can say 2n over sigma, right, is greater than or equal to 2n over 4, which is greater than 2n minus k. I think maybe this is maybe does this make sense? Now you don't have to worry about this. If it works for sigma, it works for 4.
Yeah.
Okay. So you do this, and now yeah. So now the point is what? Now you get this, and now this tells you that k is less than uh 2n minus floor 2n over 4. Great. So um good. So maybe we can call it floor n over 2. Um, so this is what we wanted. Um, um, good. So now we can go here. We can fix this. So this is so you want strictly less than um n over sorry 2n minus n over 2, right? So let's just say, what does this tell us? So this tells us that um so what have we done? We've shown that um so yeah, so maybe I want to be a little bit clear, right? So it looks like we've shown that if it doesn't get stuck, then okay, so we need to be careful. So what we've shown is if sigma gets stuck, um, at sigma greater than 2, then either k is less than 2n minus n over 2, or um, yeah, so maybe you can because you want to show that K has this inequality here, right? So how do we get the left side? Does it make sense what I'm saying?
Um, I think what we did was,
So yeah, what's the conclusion? Maybe we can say what is the conclusion here?
yeah, if it's less than, if 2n minus k is less than the segment, then it should work the least segment. Because because we assumed that that was the state it was stuck, that it was stuck. So when that segment is the rightmost segment, uh, I mean chain, two chains will be combined. So
Okay, I see, I see. Yeah, so this is good. Maybe the one thing we need to show is that maybe if K is bigger, right? So we still need what we still need, I think, is this, right? So what we need now is if uh, K is bigger than or equal to 2n minus floor um, n over 2, then um, then you can get stuck, right? You need to prove that this is possible. Does it make sense what I'm?
yeah, uh, we just put four chains, and
Okay,
like
good.
we said earlier, and that should work.
Okay, great. So yeah, you do this. Okay, so all have size n over 2 or n over 2. Okay, great. Good. So then I think it's done. So yeah, so I think you need three parts to make have a complete solution. So one is you need uh you need this construction for k less than n. You need this construction for k bigger than this bound, and then you need this argument, basically with this monovariant. So sigma is a monovariant because it's always decreasing for k in between these two. Okay. Okay. So yeah, is it clear how you would write a formal argument for this one?
Yeah.
Yeah. Okay. So let's see. Are there any others you would like to see what like some kind of formal argument for? Okay, well, maybe let's just go over the idea. So for number 3, what's the idea? So this is IMO 2023. Maybe we can go over it briefly. So what is the idea for this one?
Um, I'm not sure why it's in the combinatory section, but it's just simple number theory.
Okay, yeah. So I guess so I put it there for maybe. Well, maybe you can tell me what the solution is or what the main idea is.
Yeah, so if we have more than one prime in the factorization,
Uh-huh.
then there would be uh, okay, and let P and Q be the least two primes dividing n. So the
Uh-huh.
first factors would be P squared until some power P alpha, such
Uh-huh.
that P alpha is less than Q.
Uh-huh.
and then Q, and P alpha will then divide Q, plus um,
P
plus whatever
alpha.
is, or yeah,
Okay, and then what?
and then P alpha minus one will then divide P alpha plus Q, or if we only have one part P, whatever numbers.
Is this right?
Yeah,
But so this is if alpha is bigger than or equal to 2, right?
yeah.
Okay, and then in otherwise?
Mhm. Actually, I used some other proof,
Oh, I used a different
other
argument.
approach. Yeah.
Okay.
So can we just okay? Can we just try to see um D1, D2, and okay. So uh, I just want to check the problem. Um, so D of K divided by K minus 2 divides D of K minus 1 plus N, right?
Uh-huh.
And since it divides uh, N, which is D K, then that means it divides D of K minus 1.
Mm-hmm.
This now um, since divisors come in pairs, we also get that D of 1 divides D of 2. However, wait. Um, actually, D of 2 divides D of 3.
Mm. Okay, yeah, good.
And this gives us that D of 2 divides D of 4, and we can keep doing this, proving that D of 2 divides um, all um, divisors.
I see.
And now, since D2 is a prime, we can't have any other prime.
I see. So actually you've given me two proofs at this point. So actually at this point you're done because of what you explained earlier, right? Because you explained earlier that if alpha is at least 2, then there's a problem like this. And if alpha is 1, this is already also a problem, right? Because you derive D2 divides D3.
Yeah, I think the previous argument is not needed.
Yeah, so yes, actually I think at this point you're sufficient. But
Yeah,
the other thing you were saying, so okay, then let's at least finish it. So then therefore, okay, so therefore,
yeah,
um,
we can either use that, or we
therefore,
can just ignore the previous argument and um, prove
yes.
that D2 divides all divisors by
So
induction.
I see. So solution number 2 will be you have to go by it. So claim is that D2 divides dr for r at least 2, and the proof is by induction.
Okay, so first we know that divides D of 3.
Uh,
Um,
okay.
okay,
Mm,
suppose it divides D of K,
because you want to say, okay, so d
or
of,
all D less than or equal to K. And then it should also divide D of K plus 1, because um,
so okay, so base case, and then, so
uh,
assume d2 divides d3 all the way to dk. Um, okay, great. And then you have an argument d2 divides dk minus 1, which divides dk plus 1. D2 divides dk plus 1. Uh, okay, yeah, I think something like this. So I think it could. Yeah. Okay. Very good. Yeah, so this is the argument, right? I think the one you just explained.
Yes.
Okay. Good. Yeah. So does it make sense? Yeah. So I guess one thing to get full points, maybe I'll make some 1 point. So to get full points, you have to say n equals p to the r works. I think you have to write this statement somewhere. Uh, but okay, good. Okay, good. Uh, good. Yeah. So if you write n equals p to the r works and you give one of these two arguments, then you'll get complete full points. Okay. So yeah, I guess Kareem, you asked why did I put this in the combinatoric section? The only reason I put it in the combinatoric section is because you need to consider the smallest prime. So it's the extremal principle. Um, okay. Um, okay. So let's. So does the solution for this problem make sense? Should we go to problem 4?
Yeah.
Okay, so let's go to number 4.
Can't we just go to 7?
Oh, okay. So you want to skip 4, 5, and okay. I want to make sure that uh maybe let's do number 6. I think number 6. I want to make sure that we have the correct. Yeah, maybe one of Abdullah or Kareem, one of you can explain how you solved number 6. Uh, yeah, I want because yeah, I want to make sure that we have the correct argument.
All right, so first we can prove that uh, the placement of the square of the empty square doesn't matter because we can just move rows or columns to the other way from one side to the other, and
Wait,
it wouldn't change a thing.
so sorry, I don't understand. You can assume what?
You can assume this. You can assume the square in the empty square is in touching one of the corners.
Um, you can assume that the empty square. So you want to assume that all the corners are empty, or at least one of the corners is empty?
Yeah, I just want to make it in some corner to make it easier to draw.
Okay, okay. So
Since if it isn't in a corner, we can just take one of the rows above it and move it to the bottom, and it won't change anything.
okay, so you're saying if I have a valid configuration of okay, so is the claim like this? If I have something like this, where this is empty and this is something, then if this is peaceful, then the following is also peaceful. So now I have the same thing here, and I move the empty one to the. Is this what you're saying?
Almost. But yeah, we
Uh,
can just move the square wherever we want.
okay, okay, okay. So then what do you do?
I'll just put it in some corner to make drawing it easier.
Okay,
Um, okay, now can we draw it?
yes. So you are putting a rook here. Is this right?
Um, the empty square.
Oh, the empty square. Okay, I see. Uh-huh.
And like it to be a bit bigger.
Sorry?
Can we just make it a bit bigger?
Oh, I see. Okay. So which one should I make? So actually, are you explaining for me the extremal configuration?
Um, mm, Not necessarily.
Okay, I see.
Um,
And so you would like something so you would like this, I guess, or something?
yeah, so but can we just make the empty square a bit bigger?
I see. Okay.
Okay, now we can divide it into areas. We can just extend the lines of the empty square
Uh-huh.
and divide the, yeah, so now in the
Ah, I see. So you're saying this is K by K.
or
Now I understand. Okay, I see.
yeah,
I see. Now I understand. Okay. And then what do I do?
I think you can just prove, just say what the maximum number we can of forks we can put in the upper right section and the bottom left section, and then see how many we can put in the last section and see if that equals n,
I
or
no,
when
okay.
that equals n.
I see. I see. So now I understand. So you're saying we should take this K and okay, so you're saying we should okay, now I understand. So we should take this n by n. Okay, so and we should divide it into K by K pieces. Um so each of these is K by K. And so in
Mm.
total we have n over K
Um,
maybe
this is not what I
ceiling.
meant.
This is not what you meant.
No, I just want one square k by k, and first doesn't matter.
Ah, okay. I see. I see. Okay. Uh-huh. So you're saying like this?
Yeah,
Uh-huh.
and then can we just check the um, okay, so we have the length of each of the um, sections uh, next to the empty square, k times n minus k.
Mm-hmm.
Now we can put a maximum of the minimum of k and n minus k in this rectangle in each of these.
Can put at most um the max of K and n minus K. And why is this? Because you
Um,
can put one in each row and one in each column. I understand. Yeah, okay.
yeah,
So that,
and then for the last uh, square, we will have the max of these minus the minimum.
so for this one, you can put how many?
Um, Max of k and n minus k minus the minimum of k and n minus k.
Minus the minimum of K and n minus K. And why is this? Um,
Um, um, yeah, actually, I may be mistaken. It's just n minus k minus the minimum.
okay. Um, okay, but then what do we do?
Um, Now we should just see when this works. So the total number of works we can put is 2 times the minimum plus this, or n minus k plus the minimum of k and n minus k.
So is this, do I have the correct expression here?
Um, and now
Ah, I see.
we have the minimum in each of the rectangles, not the maximum.
It's the minimum. I see. Yes, yes. So
So
now,
we get n minus k plus the minimum.
great. And is this the
So the minimum
expression?
should be at least k.
Okay, so the minimum
Should be
is
k.
is do I have is my inequality backwards? I want to say like maybe it's like this, right? So uh,
So the minimum should be k. So k is less than or equal to
it's
n minus k. So we get that k is at most n divided by 2 floored.
hmm. Okay. So now I think I'm not sure if this is the answer. So
We
let
just
me.
have to provide some construction.
Uh-huh. So um. So actually, I think this is not okay. So maybe you can explain how. Okay, so I think this is true. K should be at least n over should be at most n over two. But what is the construction for n over two?
We just do what we did before. I think any construction would work, but
So so
um,
so I guess okay. So I think we have to be a little bit careful here with this with the quantifier. So um you need to prove that. Yeah. So
we
so
can
the,
just split into the case of n being even and being odd. So when it's even, we just have um, k equals n divided by 2, and the rectangles, two rectangles will be 2 n divided by 2 times n divided by 2 squares.
yeah.
So
So,
we can just put
but
n
I
divided
think I
by
think
2
so. I think I want to.
roots in the.
So there's a problem here, which is the following. So um. Remember, you want to, let's look at the, do we have the problem? Maybe I can pull the problem. So, um, okay, I need to look at the, uh, uh, okay. Okay, so basically in the problem, you need to show, what you want is, okay, so you're claiming that, okay, so let me understand this correctly. What you're telling me is, so this is the claim. The claim is that if, um, K is less than or equal to n over 2, then there exists, um, sorry, not then there exists, then for any configuration of n rooks, no, for any peaceful configuration, there is an empty k by k square. So you see that there's, yeah, so I think what did you let's see. So
Oh, okay. I think I misunderstood the problem.
yeah, so I think it's a little bit different, right? So yeah, so let's put this here. So yeah, so I don't think it works for so yeah. I think it's a little bit trickier, right? So let me come up with an example. Um, um, maybe for 4 by 4 or something, there's some kind of example, right? So even 3 by 3. So mm, no, 3 is too small. Maybe 4 by 4. Uh, so this is n equals 4. And now I think if this is your rooks, actually there's not even a 2 by 2 configuration. There's not even a 2 by 2 empty square. So if you're here, you can only say k is at most 1. Does it make sense what I'm saying?
Yeah.
Yeah, so you have to be very, very careful with this kind of thing. Yeah, so what are we looking for? We're looking for the largest k, which is what I've written here in with this red question mark, so that whenever you have a peaceful configuration, there must be an empty k by k square. Mm. Mm. Yeah, okay, so any ideas how we can solve, or even any ideas what the answer is? Yeah, okay, so maybe we can do some small cases. I think it would be useful. So let's so n equals 1 is maybe not very interesting. Maybe we can skip n equals 1, it's not useful. Well, okay, if n equals 1, then k equals 0, basically. So if n equals 2, now what happens? Now no matter how you put the rooks, the best you can get is an empty square of size 1 by 1, so k equals 1. N equals 3, I think it's the same situation. So again, k equals 1, you can get at most a 1 by 1 empty. And n equals 4, I think once again, yes, because of this configuration, it's k equals 1. Does that make sense?
Yes.
So for all of those, it's k equals 1. Maybe let's look at n equals 5. Um, so for n equals 5, now what do we do? So yeah, so what is the game we're playing? We're trying to put in the rooks so that we don't have large empty spaces, right? So somehow we want to spread out the rooks. Um, so Yeah, so any ideas how we can place the rooks? So any suggestions for how to place the rooks? Well, actually, well, what do you think K? How small can you make K? Is maybe the first question I'll ask. Does the question make sense?
Yeah.
Uh, Abdullah, does the question make sense?
Yeah.
So okay, maybe is K equals 2 possible? So can you place them so that the largest square is 2 or smaller?
Um, I think we can find a placement where the largest is 1.
1. So you can get 1, you're saying.
No, no.
But
Anyway, if I had to guess the solution, I think it would be related to the square root of n.
ah okay, so maybe you can explain that. So yeah, why do you think it's related to the square root? Yeah, maybe that's
And now let's take um, the bottom k squares.
mm-hmm.
Now for there to be, or the bottom k rows, so for there to be a k times k, um, we should have one square per k um, per k columns, or one row per k column.
Sorry, I don't understand.
Um, so to not have any k times k, um,
Mm-hmm.
to not have any k times k squares, we will need one square per k, so at least one square per k um, columns.
I see. So you're saying wait, do you want to have it like this or like I'm a little which one? How do you want to have it?
Yeah,
Okay, so like this, and you're saying maybe like each of these will have, is that right or?
um, not quite.
Okay,
I
okay.
think the distance between any two rooks should be
Ah,
at least K.
at
Uh,
least or at most?
Depending on which we want.
Yeah, let's I think uh yeah, so maybe which one do you want right now? Are you trying to um are you trying to create a configuration with a lot of empty squares, or with k by k empty squares, or are you trying to prove that there's always an empty square? Right? So for example, there's two things that you're always trying to show that trying to show that for k small there's going to be a large empty square, or the other side you're trying to do always is you're trying to basically construct
Uh,
uh, a configuration with no k plus 1 by k plus 1 empty
yeah,
square.
I think we can do both.
Okay, you can do both. Okay, so what's the idea here?
Um, so if n is less than k squared, I think,
Okay, let's start with that.
it shouldn't work.
Okay, so if n is less than k squared, um, then um, then so then what should we should say?
Actually, with or equal, I think.
Okay, less than or equal to k squared. Okay,
Then there would be a construction that with no k times k squares.
so okay, then we construct a configuration with no k by k empty square. Okay, and how does this go?
We just keep placing squares with a distance of k.
I see. So
We
yeah,
can just
so
shout out left square.
so maybe here's my question. How do you make sure you can always place at a distance of k? Because the problem is you cannot do some configuration like this, because
Yeah.
this is not going to be peaceful, right? So you have to be a little bit careful. So the idea
Yeah.
is correct, but you need to this won't
I
work.
think we can just shift the uh, keep shifting it by one.
Yeah, so you want to
Uh,
keep shifting by one. So maybe
I
where do you
think
want to start? Like where is your first rook you're going to place?
first k rows.
Um, so
I
first
want
K.
distance between each to be k.
Okay, so where should I place my first rook? Should I place like this? Yeah, so this is maybe at 1 comma 1, and
Yeah.
then 2 comma sorry, then maybe you want to do
And we
some
keep doing this until we get to
k
the
plus
end.
k plus 1 comma 2, and the claim is this. So the last one will now be okay, so it decreases by k each time, so the last one will be 1 plus k minus 1 times k
Um,
comma k. Is that
and
right?
then I think for the next k rows we can do the same but shift them one cell to the right.
I see. So then we start at 2,
And
yeah?
if the last cell is out of bounds, I think we can just ignore it.
I see. So um good. Let's make sure we understand the precise number. Um so mm, Okay, so now I'm a little. So there's something I don't understand about this construction, which is now. Yeah. So will there be rooks here? You're saying there doesn't have to be, right?
Um, I said we can just
Yeah. You can just maybe this is empty, right?
keep
So
shifting them by one to the right.
yeah. Okay. So now. Okay, great. So how do we make sure that this actually works? Um, hmm, hmm, okay. Okay, so let's yeah. Um, so I can't figure out right now if this gives you the exact bound, but let's talk about the other side. So this is a construction, and I'm not sure if it's exactly is it exactly n equals s less than or equal to k squared?
And I'm not sure.
Okay, let's maybe okay. So let's we have to figure out what the exact number here is. So this is approximate. But maybe let's talk about what is the other side. So what is the other bound? So this is a construction that has no empty square. Um, now, how can you show that the other side, right? That maybe we want to show want to show um, if k is maybe if okay, we don't know exactly what the number is, so maybe about if k squared is less than n, um, then there exists, then there always exists a k by k empty square. So how can you show this?
Um, not the. Oh,
Sorry?
okay. I think we. Yeah, I think we can do this. Um, by also taking the first k rows.
Uh-huh.
Um, and um, if we try to distribute the k rooks, um, actually maybe it's k times k plus 1 or something like that, but we can divide into um, oh yeah, so one of such places will have rook on the first on the leftmost cell, so we can just assume that we have one there,
Uh-huh.
and then to prevent and then if we assume that there are no k times k empty squares, then we should put another rook at a distance of k,
Mm-hmm.
at most k.
Mm-hmm. So k plus 1 less than or equal to k plus 1. Yeah, so you're saying that there's something okay, so k plus 1. Okay, so you're saying there's yeah, okay. Um, mm-hmm. So you're saying the number of rooks here, number of rooks is at least but actually you I don't think you can assume that it's on the leftmost.
Why not? We can just
Because
if it's not, we can just pick another row with the one on the left.
um
Another K rows.
so for example, it may be that so it may
Uh,
happen something like this, right? So what if you have your rooks like here and here? So they're not on the and there's some empty space, right? So
yeah.
here there's right? Now
I'm
if you
seeing that there is a rook on the in the leftmost column, so we can just pick K rows such that it's none of them
but why is there a rook in the leftmost column?
because there are n rooks and
Sorry. You're
yeah,
right. Sorry, yeah, you're right. Sorry. Okay, so then maybe why can I assume that you're saying I should pick okay, so you're saying I pick maybe somewhere
yeah.
in the
So not
middle.
necessarily the bottommost.
Okay, I see. So I pick here some K that contain yeah, okay, so I have one here, and then you're saying okay, so now I can say at least in this strip, uh so am I going in the right direction? Or you want to say in this strip there are at
Yeah.
least some number of rooks. So how will this work? I think it'll be
K, since we have
at least K.
K rows.
Uh-huh.
No, there are exactly K rows.
Exactly K. I see. So what you're saying is because there's exactly K, but this number should be less than or equal to however many I can fit, like this, right? Is that the
Yeah,
idea?
so if K squared is less than N, then we can find a square of K squared, K times K.
Uh, let's see. Hmm. Hmm.
Since each point can only cover like uh, K columns, so K squared is the limit.
I see. Hmm. Yeah, very good. So you're saying I have K by K, K by K. That's right. Yeah, okay, good. Yeah, so if K squared is less than N, yeah, you're saying yeah. So maybe we can say it like this. For each rook in in these K rows, mark the column and the next K minus 1 columns containing that rook. So yeah, for each rook, you mark the column containing that rook in the next K minus 1. And the point is those have to cover all N, right? Is that the point?
Yeah.
Okay, but maybe there's a way of saying this that's a little bit, okay, maybe you can say this a
Now
little
we
bit more.
just need construction for K squared is greater or equal to N.
Right, so okay, so let's speak. So you're saying if K squared is less than N, yeah, so this shows if K squared is less than N, then no, but yeah, so this shows if K squared is less than N, then there's always an empty square. Okay, and then let me just make sure it's correct. So, yeah, okay. And then you're saying if here, if k squared is greater than or equal to n, um, um, yeah, but so um,
I think we can just start with the construction as um, bottom left corner, and then we
mhm,
move k steps uh, until we get out of bounds. Then we get to the next row and put on the second column and keep moving k steps.
mhm,
And since k squared is greater or equal to n, then um, it should work.
yeah, okay, I see. Um, yeah, okay, so there has to be some kind of argument here, but yeah. So I think this construction works, and yeah, maybe is it the same as the following construction? I think if we just take we take um k by k blocks, and then we put them like in the. I think for your construction, there's going to be one rook in every k by k block, right? Is that right?
Yes.
Yeah. So I think so. We start with the k by k block, and then we put yeah. So that and then you move like so here. So in maybe we'll say like this in block A comma B, the rook is in spot A comma B. Is that maybe that's correct, right? Maybe B comma A, right? Is that better? Yeah, is that right? So if you look at the so for example, this is block 1, 1, and it's in 1, 1. But then when you go to block 2, 1, the rook is in position 1, 2. Does that I think that's your construction, right?
I'm not sure, but I'm not uh,
Maybe it's not true.
uh, not sure, but I'm not dividing it into k times k.
Ah,
Just
it's
uh, about the number of rows. It wouldn't be always k. To be a bit less sometimes.
mm, mm. Yeah, okay, so yeah, maybe I'm not understanding. Um,
But yeah, we should at least find one point in every k, k times k square.
mm, mm.
Um, I think we can just say that um, that a square in the first k rows won't work, so we would have to make it higher. But then prove it wouldn't work in the next k uh, uh, one step higher and keep doing this.
So actually, all I'm trying to understand is like what is the locations of the rooks, right? So because for this one, we just have to give a construction for this step, right? So I'm just trying to say what is the location of the rook. Um,
Um, all right, so we will have um, there should be, we can just say uh, h equals um, n divided by k or something like that.
mhm.
I don't know. And it should be I think the second layer of points would start um, at 2, h plus 1,
So h is equal to n divided by k. Is it
float.
4? Okay, so now you're saying so here I have 1 1 and then this one it's still k plus 1 2 and so on. And then what is this one you're saying?
So we will have a h points in the first. Um, let's just call them layers or whatever.
Okay,
So in the first layer we'll have h points.
so
It should be
I see. So here you're saying I have h.
yeah,
Okay, okay. Um,
and no.
mm-hmm.
And since h is less than k, I can just prove that there would be uh, there can't be a square in with that's partially in the first h rows or that's partially in two layers that would work or more than two layers.
And so how many layers are there? Yeah, maybe because there will be some small layer left over, right?
Yeah. Also, I think n mod k would make some layers less than h minus one.
I see. So you want to make some layers smaller?
I think we can just can't we just find an easier way to prove this without
Uh,
specifying everything?
yeah. So well, I guess what? So you need to give some construction where there's no empty square, right? Where there's no
Yeah.
empty k by k square, and
Yeah, I
yeah,
think this one works, and to prove it, um, I think the distance between I think h string less than k is enough.
mm-hmm. Mm. Yeah, I guess what I mm,
Since if we want to make look now in the first h rows, if you want to place a k times k squares, we
mm-hmm,
will have to put it above one of the points, and that
mm-hmm.
goes to just one of the points of the next layer of points.
Okay, so you're saying okay, so here you're saying so yeah, maybe you can say it like this. So one case is so let's place a k by k square. So if and if the square is contained in one layer, then then it touches two rooks, right? Because the rooks are spaced by K. Oh, sorry, it touches a rook, not two rooks, one rook. Touches a rook. And then you're saying if it's between two layers, so if it's something like this, now what happens? Why? No, so this is the part that I'm not quite. So why does it have to contain a rook if it's like this?
I think I have some good idea.
Uh-huh.
We can prove that for every k times k plus 1 rectangle, there are 2 points inside of it.
Ah, so how do we do that?
All right, so um, so now uh, we can look at like this. So the distance uh, the distance between each layer is less than k. So if we take the k, so if k plus is less or equal, so if we take if you put the k side on the bottom and then k plus 1 to above, it should contain 2 points, I think. Yeah.
So do I put K horizontally or K plus one horizontally? Like, yeah, which
I
is it
think we can prove
wider?
it either way.
Okay, so let's put it like this. Let's say it's like this. So it's K plus one this way and K this way. So how can you show that there's two rooks?
Um, all right, then.
Ah, okay, so you're saying, yeah, maybe I don't fully understand.
Oh, oh yeah. If there's a point in the middle, then it would be enough. So we can assume that we have a point to the left or right,
Mm-hmm.
and not have to prove that there's another point.
Mm, mm. Okay, let's think. So you're saying there's a point. Mm,
Actually, maybe you can use the fact that between any 2 points, there would be a point uh, under them and a point above them between the like take any 2 points
mm-hmm.
um
To any two of the rooks, you're saying?
any two consecutive rows.
Okay, so I take two, so something like
Uh,
this and like this.
yes.
Mm-hmm.
Okay, so if we get down, we have another row between them less than a um less than k rows under them, or sorry.
Mm-hmm. Yeah, so I didn't understand I didn't understand. So I take these two rooks and then what?
And then there's look at the rook under them.
So this one here.
Yeah, so um, this is less than yeah. So this is less than k rows under them.
Mm-hmm.
So if we try placing a square of k times k under those 2 points to avoid them, it will contain this one.
Okay, so you're saying, okay, so you're saying, okay, maybe let's start like this. So first, when we're placing we're picking a k by k square. Okay, so to pick a k by k square, we need to pick first, say, k columns and k rows, right? And now what we can say is that, we pick a square, k by k square, and we can say the columns, no, but now I have to be careful, right? We're saying if the columns are like this, um, uh,
Um, I think we can just say that we'd have to pick it above one of the points, and then prove that would contain one of the 2 points above the point.
okay, maybe we can, okay, so maybe we can say something like this. So let's just do this. So let's have this. I think the following should work. So, um, let's look at the bottom left corner of the square. So this will be, there will be an h by h block. So this will be h by h. This h by h block will have a rook, and the square will have bottom left corner here. Let's say, right? So this is to avoid containing this rook. And now you look at the h by h blocks here. And what is the claim? So, um, let's yeah, so the claim here is actually, let's see, was- so I think the point is if I took an h by k, it would be forced to contain it. Is that right? Because so the next one
Can we pick the point to be under the square?
under the square.
That would
Okay.
be easier.
Okay, so you want to have it like this. So like this.
Um, this works. So we have the point next to it after k points.
So
Sorry.
this is
Yeah.
inside, yeah. Okay, so this is good. And then the other case is
Uh, yeah, the point being at the top.
yeah, so then the other case you have to deal with is like this. So it's like, so you have an h by h, and we have the red one, the rook here. And now the other case is where this guy is like this. And then what? So now what's the idea? So now the next one will be over 1 and up by h. Is that right?
Yes.
And again, yeah, so again, it should contain it, right? Because Yeah, so actually, even if it was h by k, it would contain it. Is that's right, right? Even if it was h by k, it would contain it. And the last case is, yeah. So and then the last case is where you have maybe we can duplicate this. So the last case is something like you have an h by h, and then now you have to draw all four. This is it's like this, right? And now you want to argue that it contains. So there's one here. That's k and 1. There's one here, which is h and 1, and then there's here that's like this, right? Okay. Good. So I think, okay, here's what I'll do. I think this is actually a little tricky to even write the complete argument. So for homework, what I'll assign is all of you should write the solution to this problem, because it's a good exercise, because the solution to this problem is actually tricky
Yeah.
to write it completely. Even with the discussion we've had so far, I think there are some details that you should work out on your own, and you should write a complete solution and send it to me for this problem, because I think this is the kind of problem where people get like 4 out of 7 points or 3 out of 7 points because they don't write the solution correctly. Yeah. Does that make sense?
Yeah.
Yeah. Okay. Yeah. Yeah. Abdullah, is that okay with you?
Yeah, okay.
Okay. Yeah. So that's 1.5 hours, but So do you guys want to spend some time doing number theory now, or should we put that to Friday?
I'm kind of exhausted, honestly, and
Yeah.
I think we should just leave it till Friday.
Okay. Okay. Good. So yeah. So let's yeah. Okay. So we'll do that on Friday. Good. Okay. So yeah. So for homework, I guess write the solution to this problem. And yeah, and we'll discuss some of the number theory problems. Good. Is there anything else people would like to discuss before we break today?
So the homework is just to finish writing the solution for